So our next speaker is here from Aalto University. You are a postdoctoral researcher in the Wilma Center of Excellence. So moving away from species mapping, now we are going to go to a completely different world of material science and hear from you. Thank you very much.
Yes, thank you very much for the introduction. So, yeah, I'm Hilda. I'm here as a representative of Aalto University in Espoo, Finland. And I'm also a core member of Climate AI Nordic since a few months back, representing Finland. But originally, I'm from Sweden, so this is sort of a return home for me. Let's see. Yeah, I'll do that instead. Yeah, so in Finland, I'm a part of this Center of Excellence that is called Wilma. It stands for the Virtual Laboratory for Molecular Level Atmospheric Transformations. So as you hear from the name, the scale of what we're going to look at in this talk is a bit different from the other two. Wilma is made up of researchers from 4 Finnish universities, 2 in the Helsinki metropolitan area, and then we also have Tampere University and University of Eastern Finland. And we're also supported by the National Center for Supercomputing and funded by the Academy of Finland. So the goal of Wilma is to, by 2029, work on integrating data-driven methods into the study of atmospheric chemistry. And as part of this goal, we also want to create digital twins of many of the instruments that are being used to study this chemistry. And a lot of the research in Wilma is more on the basic science side. So we are focusing on the particles that cause pollutions and that affect the global radiative forcing. But what we want to know is what is their composition and how do they form. And in particular, we focus a lot on the organic matter in aerosols because a lot of that is very unknown. Organic compounds, they enter the atmosphere through emissions from industry, consumer products, agriculture, but also from natural sources, just like the forest. And in the atmosphere, there are reactive species like radicals or ozone that transform those emissions into more complex compound space. And that compound space is very, very large. And what is known is that a certain subset of those compounds, they take part in particle formation, and we end up with these particles with unknown composition. And the challenge in studying this is both a problem of scale, so there are so many different compounds that we want to map, but also that those compounds exist in the atmosphere at very low concentrations, which makes it an experimental challenge to study them in the field. And so many groups in Wilma have a long tradition of studying this problem already, using both computational and experimental methods. The experimental studies, they can be done as field campaigns, measuring directly in the atmosphere, or you can do it in the lab while simulating atmospheric chemistry. There are also many groups in Wilma that have worked with atomistic modeling to study cluster formation and atmospheric chemistry. Those models are typically very accurate, but very computationally expensive. So what we want to do with Wilma is to integrate data-driven methods into this study to both assist in experiment design and data analysis. And central to our research question, at least in my group, is what is in the atmosphere. So that's sort of at the heart of what Wilma is trying to get at. And to actually do compound identification, and we have a number of instruments that we can use to do that. So in today's talk, I will give an example of a study that we did so that you can sort of understand a bit of the type of data that we're working with and sort of the use cases that we can see for machine learning so far. So what we will look at is machine learning for chemical ionization mass spectrometry data. So there are many different parts to that name. But as you can see in the schematic, the idea is that you have your compound that ideally you capture from the atmosphere. And then what you need to do in this workflow is that you need to give the compound a charge for it to be possible to measure. And that's what the chemical ionization part of the name centers on. Chemical ionization means that you basically let an ion come in contact with your molecule, and then it will either form a cluster or do a charge transfer so that the molecule gets a charge. And when it has a charge, you can register the mass to charge ratio in the mass spectrometer, and what you get out in terms of data is different signal intensities at different mass to charge ratios. But as you can sort of see, as indicated by the diagram in the slide, is that depending on which ion you chose to use in the ionization step, you will get different signal intensities, and you might not even get any signal at all. So this is sort of something that at this point you would either need to do computationally costly atomistic modeling in order to sort of understand how will this ion interact with my possible atmospheric compounds, or you do testing, and this is very time consuming. So this is a use case where we wanted to see what we could do with sort of data-driven models instead. And this work was led by Federica Bortolussi, who is a PhD student at the University of Helsinki. And what she had was data that had been collected by a chemical ionization mass spectrometer for 4 different reagent ions. And as you can see, there are 2 ions that have a negative charge and 2 ions that have a positive charge. So we can sort of expect these to function a bit differently when they interact with the molecules. Right, exactly. So what Federica wanted to do then is to take the molecules that we expect to find in the atmosphere. We transform them into a descriptor, which is a way to represent the molecule to these different machine learning models that we can use. In this project, we applied a random forest model in order to, in a first step, be able to say, do we expect this molecule to be detected with this ion at all? So that was sort of goal number 1. And we did one of those models for each of the different ionization types. And I will later also show an example of where we tried to actually get the signal intensity as well. So to give you an impression of the type of data set that you will find in chemistry when you are working with machine learning, this is a good data set of 700 instances. We had 700 compounds that had been measured by this chemical ionization mass spectrometer. Those compounds are pesticides. Pesticides exist in the atmosphere, but are not a major fraction. But what is good about pesticides is that they exist in standard solutions, which most atmospheric compounds do not, which is another challenge that we have in studying them. So if we talk about what's representative in pesticides that also applies to other type of atmospheric compounds is that we have a lot of these organic carbon and hydrogen atoms, also oxygen, nitrogen. But then as you see in this central plot, that is just there to give you an impression of the type of elements that are found in this pesticide data set, we also have a whole bunch of other elements that are not as common in other atmospheric compound classes. And you can also see that in the center figure, we sort of counted how many of those different elements are found in the molecules that were detected by at least one of the ionization types that we had. And in blue, you have the counts in the molecules that were never detected by any of the ionization schemes. And so what stood out to us here was just that none of the compounds that had tin in them, for example, were detected by our ionization schemes. And then in the right side plot, you have instead the number of molecules that were detected and not detected by either of those 4 ionization schemes that we are looking at here. So you can see that for the negative ions to the leftmost, we have more undetected compounds than detected ones in our dataset. And the case is the opposite for the positively charged ions. And so already here you can sort of get an indication that these ions are interacting with the compounds in different ways. Yeah, so probably not many of you are familiar with how we work with molecules and machine learning. So this is a slide that shows a subset of the many different descriptors that you can use to represent molecules to machine learning models. There are 5 of them. So the first one, we just collected a bunch of molecular structure properties. And then there are 2 that are binary fingerprints, the topological fingerprint and the max fingerprint. The topological one is an agnostic one to the molecular structure in the sense that it only traverses certain paths inside the 2-dimensional molecular structure, and then it converts that into this series of zeros and ones, while the max fingerprint, it has 166 keys that corresponds to yes or no answers to questions regarding the molecular structure. And then we have 2 descriptors that are 3-dimensional, in the sense that they also capture the 3-dimensional structure of the molecule. So that is also an interesting dimension when you're working with this type of data, because that can give you some information about how well that molecule is going to interact with the ion in our case. So this is some results from our classifier models. Here you see an example to the left of a negative ion and to the right of a positive ion. On the y-axis you have the true positive rate, and on the x-axis you have the false positive rate for the classifier. So a random classifier will end up on the diagonal in this plot, while a perfect classifier would only be located in 3 areas of the plot, which is the downmost corner, uppermost corner to the right, and the uppermost corner to the left. Because what this plot is showing is basically how the classifier sorts the data depending on different thresholds. And we can see also that the area under the curve metric is shown in the legend, and you see that we have values between 0.7 and 0.9 for both ionization types. So we are quite happy with that in terms of our goal of being able to determine whether a molecule will be detected or not by these 4 different ions just based on their structure. And what's interesting is that we don't see a particular advantage for the 3-dimensional descriptors. And if we look at all the different ionization types that we were looking at, we have a classification accuracy that is quite similar across all 4 different ionization schemes. We also wanted to see if we could get some chemical insight from our model, because this model would then, in a use case, sort of compete with this atomistic modeling, where you're actually getting a molecular insight into how the interaction is looking between the molecule and the ion. And so here, just analyzing the random forest model, we see here the 13 topmost important features when we trained our model with the max fingerprint. And for the negative ions, we saw that NH and OH groups come up as the most important features, which is also chemically intuitive. And for the positive ions instead, it was the presence of nitrogen and how nitrogen was bonded to the other atoms that was the most important. And then looking at signal prediction, we took the data only of our molecules that had been detected for each of the different ionization schemes and tried to predict the signal. And you see the mean absolute error in log scale on the y-axis. And these are our learning curves. And you can see that the model is learning for these 2 different descriptors and for all different ionization schemes. But what seems to be determining the final error is more what ionization scheme we are looking at than increasing our training data size. And so this is probably one of the problems that arises with working with these small data sets that we have in chemistry. The best performing models are those for the positive ionization schemes that had the most detected molecules as well. So to sort of conclude this talk, we were quite happy with this study as a demonstration of how we can use machine learning to sort of assist in experimental design in atmospheric chemistry. The signal prediction is within 1 order of magnitude, but there we really see that if we had more data, we could probably do it better. And we can also get some chemical insights, so this type of model can still be useful as an alternative to atomistic modeling for those purposes as well. But if you want to then take this model and start using it, certain things you would need to add are, for example, concentration effects, but that is quite easy. All the data was here collected only in one concentration. However, the big problem that we're facing in general in Vilma and in this type of study is that these signals that we are trying to model, they are highly variable. And if you talk to an experimentalist, they will say that not even in their own same lab do they expect to see necessarily the same signal patterns, while the detected versus non-detected is more robust. So looking ahead, we aim to work with machine learning for compound identification with mass spectrometry data, but we really need more labeled dataset for atmospheric compounds. And so in Vilma, a lot of the groups are looking towards simulated data with atomistic modeling as a solution for the lack of experimental data. And with that, I thank you.
Thank you very much for the exciting talk. Do we have any questions?
Thank you. I was just wondering, have we considered using graph neural networks for embedding representation?
Yes, you can do that, but we typically consider that more for larger data sets. This was so small that we did not even attempt a neural network.
Do you have any insights or ideas on why the descriptors that do encode the 3D information, they work the worst?
Yeah.
Do you have any ideas on why that's the case? Do they have anything that's lacking from the other descriptors or something else?
Yeah, so the clear standout is more the Coulomb matrix, and in particular the Coulomb matrix for the bromide case, so that's the yellow line there to the left. And the Coulomb matrix, it sort of implicitly encodes the atomistic types through the Coulomb interactions between the atoms, and perhaps the information here and combined with the small data set, it becomes a bit too implicit for the model to learn from, while the two-dimensional ones are really explicit and perhaps a bit easier. Yeah.
Yeah, thank you. So I had a question that's essentially a follow-on from that. Maybe I missed it, but I wonder how complex these feature representations are, like how many features in each one.
No, I didn't mention it. So it can really vary. The smallest descriptor that we had here is the one that we call RDKit prop. That was a collection of 40 molecular structure properties. Then the max fingerprint that is doing really well in our study here, it has 166 features. And those are sort of hard-coded questions about the structure. And then the largest descriptor is MBTR, which is an encoding of the three-dimensional structure, and that typically has over 2,000 features.
So do you think the size of the feature space might be part of the problem here?
Yes, we also sort of speculated on this. Yeah.
Any last question over there?
Thank you for the talk. I was wondering how the atomistic simulations could be incorporated into this machine learning model. Because you mentioned before that you try at Vilma to incorporate both simulations and machine learning and experiments.
Yeah. So you want to know a bit more about how you would do this instead with atomistic modeling, or how you could use atomistic modeling to support this?
Yeah,
to support.
Complement,
Yeah. So if you do atomistic modeling for chemical